Okay, so this video is going to go over masses in mechanical systems. So masses, usually how we can represent them, the real thing is like a car, for example. Uh, how we draw them in a class like this, um, it would be just like a block to represent that mass. But how it's actually modeled would be a particle. A particle mass is one of the easiest ways to represent a mass. And these x and y here, those are its coordinates for its directions. So how is a particle mass represented? Well, we just use Newton's second law. So we have our mass times our acceleration vector is equal to our mass times the derivative of our velocity vector, which is the same thing as acceleration. And that's equal to the force vector, the sum of the forces in the same, that's oriented in the same direction as the acceleration vector. And note that for this case that we're assuming that our mass, m, is constant. So let's assume that our mass only moves in one direction. We can have a scalar equation of motion then. So m times a, which is m times dv over dt, derivative of velocity, which I'm going to represent in this class using v dot, that's equal to some force F. And we have things in terms of velocity of this mass. In general, masses are described by velocity. And we know that velocity is tied to kinetic energy. So there's this connection between velocity, masses, and kinetic energy. So how do we calculate kinetic energy for a mass? Well, it's all about using the conservation of energy, which is the rate of change of energy stored in a system is equal to the power flowing in minus the power flowing out plus the power generated, or the rate of energy generated. So this is the rate of change of energy stored in control volume, power into the control volume, power out of the control volume, power generated. So for our particle mass, let's start with Newton's second law, the scalar version, and multiply both sides by that velocity v. So we'll get mv dv dt is equal to f multiplied by v. We get that equation there, and that is actually the conservation of energy. And this term here on the right, that is mechanical power, which is velocity times a force. And this term over here on the left, this is the rate of change of energy in the mass. And if we integrate, we can actually find the total energy of the mass. So let's multiply both sides by dt. Let's integrate from an initial velocity or initial time to a final time, which is the same thing as integrating on the left side, initial velocity to a final velocity. We can actually figure out that we end up with this equation 1/2 m times vf, v final squared, minus v initial squared. And if we say v initial is 0 and vf is equal to v, just for a generic representation, we can get the formula for kinetic energy. Kinetic energy, Ke, is equal to 1/2 times m times v squared. So with this, we have the connection between our masses, its velocity, and kinetic energy. So how do we model a mass with an external force acting on it? Well, if we have our mass, m, and we have two forces acting on it, F1 is pushing it in the right direction, the same direction as our velocity, how it's oriented, and F2, which is pushing it in the opposite direction, well, we can have mv dot is equal to F1 minus F2. And that's it. That's all we need to do to model a mass. And that's going to cover masses.